All right, in this video we're going to talk a little bit about separating the different forms of kinetic energy. So what I have here is a baton that has two large spheres on either side and a very thin light mass rod that connects them. This baton is spun around its center of mass like this, and what we're interested in is calculating what the kinetic energy of this baton is going to be. So if we go back to our description of the total kinetic energy of a system, we will add up the different components of the kinetic energy. So the mass of the first one times its speed squared, and the mass of the second one times its speed squared. We'll add those things together. So in this case, what we're going to say is that we'll end up with mass 1 times v1 plus mass 2 times v2 squared, just as you would think. Now the interesting thing about this is that these two things are rotating, so because they're at the same distance from the center here, they're actually moving at precisely the same speed. So they have individually the same amount of kinetic energy, and so this addition is actually relatively simple. In fact, we remember from one of the last videos that we had, we can actually write down what that velocity is of each of those relative to some angular velocity that they would have rotating around this center of mass here. But we have a slightly different situation, perhaps. So let's say instead of twirling the baton around its center of mass like this, it's twirled and it's tossed up into the air. Well, if it's twirled and tossed up into the air, then it has some vertical velocity at some time, let's say. And therefore, this mass that's sitting over here, which is on its way upward, is actually moving a little bit faster than the one that is moving downward at this time. And so because of that, they're now going to have slightly different kinetic energies. These individual constituent parts will have slightly different kinetic energies. And so we want to try to keep track of those different ideas. And the way of doing that is to think about the total energy as being the kinetic energy associated with what we'll call translation, which is taking this whole thing and sort of squishing it down and letting it move upward. So this would be how the center of mass moves. So if you're following the center of mass in its motion, this translational kinetic energy is precisely what that center of mass has. And separating that out into that piece and a piece that is relative to the center of mass, which keeps track of how fast are each of these objects moving relative to the bulk motion of the baton itself. So this is relative to the center of mass. And it turns out that the total kinetic energy can be easily separated into this translational part, which tracks the center of mass, and a relative part, which tracks the motion around the center of mass, whether it's rotation or vibration. Another example of this is having a spring attached between two masses, and these masses are allowed to oscillate back and forth like this. If it's not moving in any other way, we have no translational kinetic energy associated with the center of mass. The center of mass here isn't moving. What's moving are these two objects. So there's some vibrational kinetic energy with regard to the motion of these two objects relative to the center of mass. So clearly we have two different examples of relative motion, and those are both can be kept track of in this relative kinetic energy formula. So we can think of this as rotational kinetic energy and vibrational kinetic energy. So energy associated with objects moving around the center of mass, and energy associated with objects oscillating back and forth, like in this picture. So there's a formal derivation in the notes which shows you how these two things separate out. But the idea is just think about this conceptually as the translational kinetic energy associated with the center of mass motion, and relative components that can be thought about in terms of rotation and vibration.